Good afternoon and welcome to today's little webinar. My name is Thomas Stollenberg. I dial in from Vienna, Austria today, and I work for Oikoplus. We're the company taking care of the communication and dissemination under the EU RISE project framework. And today we invited you to give you a little insight into the EU-funded research and innovation action under the name of EU RISE, which set off in December of last year with quite ambitious goals. EURISE is an exciting project that contributes to the development of future space ecosystems by launching technologies that enable the use of robotic spacecrafts for on-orbit satellite assembly and maintenance. And in doing so, the EURISE project pursues an open source strategy. We have prepared 3 presentations for today's webinar that give you an understanding of the work program of the project consortium. And at the end of the project period, which is of a duration of 18 months, an end-to-end demonstrator should be available. And at the same time, one aim of the project is to analyze the market environment for the technologies developed within the project framework. I don't want to get too far ahead of today's presenters. Let me just emphasize that today's webinar will be recorded and made available to all of you via the EURISE website and the project's YouTube channel in the aftermath. And since the project is coordinated by Airbus Defence and Space, all of our 3 presenters today work for ADS. In fact, we have among us Mark Munz, who is actually the coordinator of EURISE, who will give you a general overview of the project's ambitious endeavors. And then we have his colleagues Romain Coujol, who works for ADS in Toulouse, who will explain to you Europe's and also EURISE's vision for a future space ecosystem, and Ingo Arndts of ADS Bremen, who will take a deeper look into the technologies, the robotic technologies to be developed under the framework of the project. The mode for today's webinar is that during the presentations, we invite you to share with us your questions, because in the very end of today's webinar, we will have an open Q&A session. Because we are recording this session today, there is no comments available to you. You may have figured already that the comments function doesn't work. This is why we ask you to please use the Q&A function that comes with Google Meet. You would find this little symbol usually in the lower right corner of your browser now, with the triangle, the square, and the circle. And this opens a variety of tools, and one of them should be the question and answer tool. We will share after this event. It may take some days for us to prepare the actual recording, the link, so that you have access to the recording and then also can look again into the questions that have been raised in the end of the session. The Q&A tool of Google Meet enables you to upvote question you consider interesting. That helps us in the end to do a moderation of the Q&A session. If there's questions that have been upvoted quite some times, we can ask them first in order to have like a structured Q&A session in the end. And now it's my pleasure to give the word to Mark Munz, the project coordinator of EURISE, who will give you a little intro into what the project is all about. Mark.
Thank you, Thomas. So I will speak about EURISE project at a glance. Later on, my colleague Romain Coujol will present actually the work we did in the last 3 to 4 months. This was, we call it Workstream 1, about the definition of the future space ecosystem. And then my colleague Ingo Arndts will give an outlook to what will come next, just to sort it a little bit on the timeline. So let me first introduce to you our consortium. We have partners from all over Europe. Airbus Defence and Space, we are here participating from 3 different nations, as we have a transnational robotic team and we develop our stuff together. Of course, we have the knowledge of space systems as a large system integrator from that perspective, but this team or department we all belong to has also some knowledge and heritage for robotic manipulation, interfaces, robotic flight software and stuff like that. We have with us DFKI from Germany. They are also experts for robotic systems. They work in several fields and also in space, and they contribute to the enabling technologies, both on software and hardware side. So they will look on the framework, on application software like motion planning and stuff like that, but also the tool extensions. And then we have the exploration company with us. They are our experts for space transportation. They build a capsule to transport cargo and astronauts in the future. They led the assessment of the transportation and logistics part for the last 3 or 4 months in our future space ecosystem definition. We have Oikoplus with us. As Thomas mentioned already, responsible for dissemination and communication with a background from several EU projects. The LibreSpace Foundation, they are experts for open source strategies and platforms, and specifically in the space domain. I think this is important to understand also the environment you want to open source something, and this is why we're really happy to have them on board in the project, because one of the goals is also to create open source building blocks which can be used by industry and academia later on. We have Magellium with us. They are also robotic experts. They will contribute on the digital twin, robotic simulation, robotic perception, robotic ground console, so mostly on the software side. And last but not least, Cenair. They are the experts in our consortium for the modularity concepts. So they not just provide the SIROM interface for the demonstration later on, they have also gained a lot of knowledge about modular systems, and they were also contributing to the future space ecosystem definition in the last month with this aspect. So why do we want to conduct such a project? We want to prepare a paradigm shift to change the way space systems are designed, built, and operated, moving from mission-specific solutions to modular spacecrafts, which are serviced, manufactured, assembled by robots in space. We want to improve the capabilities, cost effectiveness, the reliability of space assets, through the use of in-space servicing, assembly, and manufacturing. We all see, and I think all of you will follow also the evolvement and evolution of the Starship, for example. So our launchers getting bigger, but still somehow our capabilities of launching or providing big structures in space are limited by the launcher capabilities. And this leads in several roadmaps from agencies or companies to in-space servicing, assembly, and manufacturing, actually. And systems like space-based solar power, space data center, and stuff like that. Also, bigger space stations are not possible, even with a Starship. We want to strengthen the European capabilities to build future orbital infrastructures, exactly those I mentioned, the bigger ones, the new concepts, and we want to be competitive on the on-orbit servicing markets. We want to harmonize robotic hardware and software building blocks existing in Europe to enable realistic robotic systems for commercial and institutional missions. So you will see a big part of the project is about the enabling technologies. As I said, there are 2 work streams, future space ecosystem definition, and the second work stream are the enabling technologies. But it's not about the development from scratch of certain building blocks. It's more bringing them together, harmonizing those building blocks, making a system out of it which works under realistic conditions. What we want to avoid is really having at the end a demonstration with a kind of an artificial busy board or something like that. We want to show that this system is able to work on a realistic business case and a realistic mission. And this will be shown with assembly tasks, but also reconfiguration. And the last point is the preparation of an open source strategy to enable more companies of different sizes, as well as universities and foundations, to contribute to the European future space ecosystem. It's a question, why is this important for us to drive as commercial players such a strategy? I think we are convinced that this will help Europe to join forces and really have a win-win situation. On one hand, the academic world and students can work with flight software, building blocks, be it hardware or software. On the other hand, those building blocks will be matured further and will be used in different scenarios, which helps at the end also the commercial players in this. The project has four main topics, four main pillars. First one is the assessment of the market and needed capabilities to serve those markets. The second one is the definition of an end-to-end demonstrator system, which allows us to provide those capabilities. And then the development or harmonization of enabling technologies, both on hardware and software level. And finally, the verification and validation of this end-to-end system. So to give you an overview of the complete projects, in these 8 steps, you have more or less the complete project summarized. So the first part, the future space ecosystem workstream, is what we did in the last month. We had our review meeting last week and finalized at least step 1, 2, and 3. The open source part is going on why we develop also the software to see what is the best strategy. So the first step, I mentioned it already, was a market assessment to identify important services, the competitive landscape, and also the market volume. The next step was to assess the needed capabilities to provide these services. And then we defined some system concepts, which you will see in a few minutes, composed of existing elements to realize the capabilities. And in the next phase, which started already, we will define the requirements and the system architecture for the end-to-end demonstrator to fit to the system concept. We will adapt and mature the building blocks to meet the demonstration needs. We will integrate all of the building blocks into the end-to-end demonstrator in our lab at the end, and verify the functionalities and validate it on a realistic assembly and reconfiguration task. So here, this reduced schedule and the activities we are conducting, you see we have already 3 to 4 months in the project to conduct this future space ecosystem definition. And now we are starting with the end-to-end demonstrator system. Of course, first with requirements and architecture to fit to this system concept. And then we start end of this year in Q3 with the development of the enabling technologies. And next year, we will integrate everything into the overall test bench and test it. So just a very brief summary of the market assessment and why we think it's a clever approach to concentrate on several or on those capabilities, and especially on assembly and reconfiguration. We see that most of the orbital robotic activities have a lot of common capabilities which are necessary for most of the missions. Because if you want to service a satellite, you want to do inspection. If you build something, you need to do the same. You need to realize at the end or understand at the end what is the as-built status. And it's actually the same for manufacturing later on. You have to handle standard interconnects, and this is also for most of the missions the case. There are some specific missions when you have unprepared satellites where something like a standard interconnect or a standard interface will not be used. But for all the other missions, it's just a way to go probably, because it's also what we see on Earth. That's the first point, and also a lot of system studies point in that direction. Rendezvous and proximity operations are important, mostly, of course, for on-orbit servicing. But if you want to assemble, for example, a reflector in orbit, and you want to install it on another spacecraft, of course, you have to do rendezvous and proximity operations or in-space docking. Then the installation of elements, it's the same. It can be an ORU on a space station, or which is maybe, or ammonium tank, which is maybe more a servicing task, but it can also be the installation of a reflector or any other element we want to assemble or we want to build up there. Then in-space transportation, this usually means bringing some elements to a dedicated orbit, and we speak mostly about spacecrafts, what a space tug is normally doing, but this is of course the same if we want to assemble for certain reasons in a low Earth orbit an antenna and want to bring it to a geostationary satellite. It's also kind of a space transportation. And then we have some specific capabilities on the on-orbit servicing part. It's more the planned and unplanned repair, upgrade and maintenance. Fuel transfer is a big topic, and resupply when you think about space stations. For the on-orbit assembly, it's mainly, in addition to the common capabilities, the handling of dedicated mechanical and electrical interfaces. So connecting some plugs, screwing something together. This is all summarized under handling mechanical interfaces. And for on-orbit manufacturing, it's really the actual manufacturing process, like printing something in space, casting, extrusion, welding, and so on. There are several concepts out there. And this is not the focus of this activity, actually. On the right-hand side, you see a summary and overview of active entities and just cluster by the different orbits. And you see actually every rare, this rare cislunar orbits, or the transfer from geo to cislunar is maybe not so often, but beside that, it's quite distributed. And this shows us also that the need for modularity is present on several levels. We have that in our robotic system. We see that in a lot of robotic building blocks. The whole standard interconnect idea is built up on that. But this is also important when we speak about modularity or adaptability to different orbits for such missions. It's not just that it is clear it will everything happen in LEO right now. And with that short summary, I would hand over to Romain Cajol, who will present us the work we did for the future space ecosystem definition. Of course, if you have questions to this part of the presentation, just write it into the question and answer session, and we will make sure we go through your questions at the end.
Thank you, Mark, for the introduction. I will now share my screen just so everyone can see it. Hope it's working now. I will present the work that has been done in this first work stream, as explained by Mark, on this Eurovision for our future space ecosystem. First, recalling the methodologies that we had for this first part. So Mark already presented it, but we went from a market assessment to try to identify the market trend and cluster of application for this future space ecosystem with a focus on robotics. And the idea from that is that we identified mission capabilities that are needed to cover these future space ecosystems. And from these mission capabilities, we derived the functions, the functional building blocks that are needed to cover the different missions that can exist in this market. And after, in the last part, we perform a concept definition. So we had different concepts that I will present to you, on which we try to implement all the functions identified in order to have a modular approach and to cover this future space ecosystem. So as Mark already mentioned, the idea here is to go from a mission-specific system to a modular system. We have seen that we have in this market on-orbit services, on-orbit assembly, on-orbit manufacturing that require a lot of mission capabilities and different mission capabilities. And we think that modularity is really a key to tackle this future space ecosystem, as it is something that moves fast, appear in different orbits, and it's hard to know where the markets will go. So modularity is key to address it. And on the left side of the screen, you can see that we first perform a functional analysis to try to identify the main functions that are needed to address this future space ecosystem. And we perform a ranking of this function to try to identify the functions that are needed to cover most of the missions. And what appear here is that the functions associated to transport and to robotics are of main importance to this market, because of course, if you want to perform a service on an assembly, you need first to reach your clients and to connect to it in somehow. And after, robotics is also a key because you need to interact with your client after that. So it's also a key. And in all the functions here, you can see that autonomy is a key topic, computer vision, docking, robotic manipulation are key topics to address these markets. But if you want to put all these functions in a modular way in a system, you also need to identify use cases to apply the mission and to verify the mission applicability. And so this is why we also perform a mission ranking analysis on the right side to try to identify the missions that require most of the functions. And by this, I mean, what are the missions where we need all the functions that we need to cover the full ecosystem. And for that, it appears that on-orbit assembly is a really good candidate because, of course, to perform on-orbit assembly, you need a lot of elements. It's a complex mission where you need all the robotic capabilities that you will need to perform a service, for example. And so that's why we selected the on-orbit assembly as a use case for our study. So based on that, we defined two different concepts that I will present to you. So we have one concept. So the two concepts can cover this future space ecosystem, of course, and both concepts are equipped with robotic systems. But let's say that we have a different term in terms of appearance in the market. And so on the left side, we have this reusable by reentry concept that is more for mid and short term. Why it is reusable by reentry? Because it's a system that is composed of a capsule where it's possible to put some elements that will be recovered on Earth after reentry and to reuse them for another mission, for example. I will present it deeply after that. And on the right side, we have another concept where we try to push more this modular approach and have a system concept based on modules that are assembled together in order to try to answer to different needs and different missions, depending on the stack of the different modules. And I will present this in detail after also. So going into the details of this reusable by reentry concept. So it's a concept where we have flying spacecraft that is composed of a capsule and a service module. And both the capsule and the service module have a storage volume in it where it's possible to store some elements. So we are talking about services and assembly. So you can think about putting some parts to perform an assembly. You can think about putting some orbital replacement unit inside it to perform a module placement on a client spacecraft or anything, or also put a robotic system inside it to use it after in space. And at launch, these two elements are attached together, as you can see on the left part of the screen. And they perform some mission in space. And after, at the end of life of the system, the service module and the capsule are separated, and only the capsule is equipped with re-entry capabilities. This means that by storing inside the re-entry module all the elements, the valuable elements like the robotic system inside it, it is possible after to retrieve it on Earth and reuse it for future mission, for example. And for that, having a modular approach also in the definition of a robotic system is really important to be able to have this kind of circularity in the use of all the elements. And for this concept, we rely on the use of this Nix Earth concept from the exploration company, the vehicle you can see on the right. So check out what they are doing. We rely on that for the definition. So going a little bit into the details, I said that both the service module and the capsule have volume for cargo to put elements in it. So we can think about using this volume to have element for assembly, for example, and to store also the robotic system. Because if we look at the beginning of the life of this system and at the end of the life of this system, let's say that in launch configuration, we expect to have some robotic system to perform the operations and also some parts for assembly or for servicing that will be stored in the cargo modules. And at the end of life, there will be no remaining parts or elements because they will be all used or installed on the clients, and only the robotic system will remain. And this is why at launch, the robotic system can be stored inside the capsule or inside the service module, but at the end of life, it is mandatory to have it inside the capsule in order to reuse it on Earth and to use these re-entry capabilities to reuse the system for a future mission. And this is what we can see on the right side of the screen, where at launch, we have a robotic system that is stored inside the service module. We launch it. We have some mission space. After, all the robotic elements are transferred to this capsule is separated from the service module and perform a re-entry, where it's possible to get all the robotic system back into a second mission, for example, to perform other mission. And in that way, having a kind of modular approach that allow to cover different kind of missions. So here it's just small ConOps presenting a kind of mission that could be performed by this system. So we consider that we will launch the capsule and the service module attached together to reach a certain parking orbit, for example. And then we can consider that with the system, it's possible to address different mission and different clients. So let's imagine that the first mission is a reflector assembly. So the system will need to reach the client spacecraft 1 to perform an assembly of the reflector with the robotic element that is installed inside it. And once it's done, it can address a different client, client number 2, where it can perform any kind of service. I don't know, repair something. Client 3 with another service, installing of a module inside these clients. We can imagine all the kind of services that were mentioned at the beginning by Mark. And at the end of this mission, when there is no part left into the cargo to perform any assembly, or if there is no propellant left inside the tank, the capsule is separated from the service module, and the capsule come back to Earth. And this is where it's possible to get back all the valuable elements, robotic elements that were needed to perform all these missions, to put them in another mission and continue the life of this system. So here is just a visual representation of what it can look like practically. On the left side, you can see, for example, the capsule with some elements stored in it, ready for a mission. And you can see that some interface are placed on it also to enable a robotic system to walk outside of this capsule and to perform some robotic operation outside of this capsule. And this is what we can see on the right side, where a multi-arm robotic system is performing assembly task. Here it's a the assembly of a reflector antenna with parts that are stored inside the capsule. And we can think that later on in this operation, the reflector will probably be installed on a client spacecraft to finish these assembly missions. So main takeaway about this concept is that it's reusable. This is a key topic because, of course, it allows to store, for example, the robotic systems that we see here back into the capsule to retrieve it on Earth and to reuse it for multiple missions. And by having a modular approach on this robotic system, it's possible with the same system to address different kinds of missions. And this is the key for this future space ecosystem. If we push a little bit this modular approach, we have the second concept that is in-orbit modular, on which we try to push the modularity to a point where the system is composed of different modules, and each module is specialized for a given task. For example, we have this tagging module that is responsible for tagging the system, a robotic module, a cargo module, and all these modules are assembled together or launched. Well, I will explain after, but it's possible to launch them together or to assemble them in space. And then it's possible also to add other modules or to exchange modules in space to have systems that evolve during the mission and is able to address different kind of missions. So here is just an explanation of the different kind of modules we foreseen for now. We know that we will need robotic modules that will contain all the robotic system, so robotic manipulators, tools, workbench to perform any kind of assembly operations or service. And of course, this needs to be also modular in a way that it needs to be possible to add new tools in the system during its lifetime, for example, to address a mission that was not foreseen at the creation of the module, for example. We also need cargo modules that will contain all the consumable specific to the mission. You can think about resources, some parts to perform an assembly, some fuel if it's a refueling mission, some spare parts if it's a maintenance mission. We will also need some ORUs, that is the acronyms for orbital replaceable units. And this is more a mission-dependent function that can be stored inside the capsule module, cargo module, or can be also a separated module depending on the size of these orbits. We will also need tagging modules that will be responsible for tagging and replacing all the system in space. And for that, we will rely on the use of unique tag elements from the exploration company that we can see some details on the right side of the screen. So just to give some insight about this modularity, the idea is that the stack of the different modules can be different depending on the mission and can evolve during the mission. So we can see, for example, on the left side, an assembly, a system just made about a robotic module and a tagging module, where a service is needed but do not require any part coming from a cargo module, for example. And after, we can see on the right side different combination of robotic modules, cargo module, tagging modules. Of course, the cargo module design can be different depending on what is transported. Here we just perform some representation of assembly of 3 modules, but it's not limited to 3. We can think about having different robotic modules to perform parallel operations or different cargo modules. Well, let's say that with this modular approach, it's possible to have a different configuration possible. And as for the other, let's say that here is just a representation of a kind of mission where the tagging system and the robotic module are launched together. And after, a cargo module is launched in a second launch and connected to the first element by whether using berthing with the robotic system or docking with the docking interface. Let's say that modularity is also possible at this point. And on the cargo modules, of course, we said that each module is specialized for a given purpose. So this cargo module have some cargo volume, of course. This robotic module has all the robotic system, and the tagging module contain all the tanks and the propulsion system to perform the tagging. So here it's just a representation, like for the other concept of a ConOps, of what a mission can look like with this kind of concept. So let's imagine that we launch a robotic module and a tagging module together. These modules will be stored on a parking orbit. And then we have a specific mission on a client that requires some service. So we will need to reach this client to connect to it, perform a maintenance mission, for example. And then we have a second mission where we need to assemble a reflector antenna on the client. And so for that, we will need some material coming from Earth installed inside cargo modules. So the cargo module will be connected to the things that are already in space. And this whole system will reach the clients, perform the operation with the robotic system, assembling and connecting to the clients. And once the mission is finished and there is no part left into the cargo modules, let's say that we can throw back the cargo modules to continue the mission. And we can imagine also having kind of missions where a client require some robotic system to perform in the future some maintenance on this spacecraft. And for that, we can imagine also that a module can also be separated and stay on the client. Like here, for example, we separate the tagging module and the robotic module to have the robotic module staying with the clients to perform autonomous robotic operations on it. And then the tagging module will be then to be completed with, again, a robotic module and cargo module to continue the mission as needed. And of course, it's not presented here, but we will need some refueling operations on the tagging to extend the time duration of the system. Because compared to the other system, the idea of the system is that it stays in space. And so it will need to have some life extension capabilities also to stay longer in space. So here is just some images of what it can look like in space. On the left side, you have this tagging module connected to a robotic module and to a cargo modules with everything stored, ready for operations. And on the right side, you have a robotic system that is performing an assembly in space. Here it's an assembly of a reflector antenna, for example, that will be later on installed on the client spacecraft. And the main takeaway here also for this concept is that we push the modularity concept in order to make sure that we are able to address this future space ecosystem with this modular approach, where it's possible to add new modules, modify modules, or upgrade the modules during the lifetime of the system. So if we look at the physical building blocks that are needed at robotic level to perform all these missions, we know that we will need robotic manipulators to move a part from one place to another. We also need some robotic tools if we look at assembly operations, for example. We will also need some workbench to grab the parts that are needed to perform an assembly. We will need also some standard interface. So here it's presented the one from CNR, Serum interface. This is needed whether to be equipped on a RUSE, orbital replacement unit, because we will need to standard interface to connect this replacement unit to a client spacecraft to upgrade this capability. But it can also be used at robotic level, for example, to allow locomotion on the spacecraft. If we place different standard interconnect on a spacecraft, it's possible for the robotic system to walk on the standard interface to be relocated where it's needed for the mission. We will also need a vision system for verification purpose, but also for accuracy purpose on the robotic system. Some robotic control unit to control all this system. And some part dispenser, because of course we are talking here about robotic assembly. And to assemble parts, we first need to store them in a proper way to allow the robotic manipulator to grab them, for example. And all this system, all these building blocks, we try to implement them in the two concepts that I showed to you. So, for example, you can see here the reusable by reentry concept, where all the building block I showed to you are present. We can see workbench, robotic manipulators, and so on. And the idea is that we try to have a modular approach in the implementation of this technology in a way that it's possible easily to transfer from one concept to the other. So here we can see the implementation on the reusable by reentry concept. And here it's the same building blocks, but implemented in the in-orbit modular concept. So you can see that the technology are the same. It's just the implementation that is not the same and the concept that is not the same. But let's say that we try to concentrate on the definition of these technologies in order to be ready to define this future space ecosystem and to have this modular approach. So this is our vision for this future space ecosystem. And I will now let the floor to Ingo to present you the development we are doing on all these building blocks. If you have some question about this part, don't hesitate also to put it on the Q&A, and I will answer it at the end of the presentation.
Okay, thank you, Romain. I hope you can see my screen now. So now I'm going to explain you what we have in mind for EURISE in our second work stream, which shall be about the robotic enabling technologies for in-space servicing, assembly and maintenance. And most of them were already introduced by Romain, but I want to show you what we want to do really very concretely in our laboratory and what we want to demonstrate at the end of this project. And this is also where I'd like to start with, to show you our vision of what we have in mind and what we want to use as a use case. And the use case we want to use is motivated by one of the outcomes of the first work stream, which was called by Romain the reusable by re-entry concept, which is shown here in the left image. You remember the robot which was able to walk over the spacecraft, and the spacecraft consisting of this capsule and the servicing module, and the cargo bay of the servicing module had a lot of elements which provide material for assembly or similar activities. This is definitely a very advanced target, and we are convinced that in between we will see definitely in the first step a little bit simpler approach, which is shown here and which could lead to what we have in mind here is to establish a kind of in-orbit demonstration. And in fact, we have in parallel running projects which are investigating this system studies on such an IODs. And we are using now this scenario from this potential in-orbit demonstration, where we would like to demonstrate the capabilities of our robotic elements in the EURISE project. So in principle, all the elements which are relevant for us will be used and will be integrated into a single demonstrator. The only thing which is missing in the demonstration we have in mind is the mobility concept of the robot. This will be has to be done then later. Okay, starting from this motivation, this picture shows how we could imagine how a setup in our laboratory could look like. So we would use this part of a kind of robotic factory consisting of several elements. We have in mind to use two different robotic arms, one dedicated really for space missions, and I will come to that later, and another one which is just for the purpose of our demonstration, an industrial robot, maybe a KUKA or a universal robot here. Beside that, we will also see objects which may come from a part dispenser, for instance, tiles, which can be used to build these antenna reflector, which were mentioned by Romain. And also other elements might be useful for this, like the standard interconnects for the replacement of orbital replacement units, and also smaller actuators might be useful as a kind of holding device, or what we call it a workbench. So this is the basic idea of what we have in mind, and the challenge here is that we want to integrate as much as possible elements which really have been designed for space, like a space manipulator, like the standard interconnect, but also the antenna reflectors, which were dedicated really for space mission so that we are as close as possible to a real in-orbit demonstration, which could be then the next step. Okay, this shall be the vision. And there's one challenge not to be forgotten, which is the fact that we have to demonstrate everything under 1G condition. So this is especially a challenge for our robotic manipulator because it is designed for usage in space under 0G, which means that it does not have to be as strong as a typical industrial arm on Earth. This means, especially if we want to move heavy payloads like different tools or elements we want to assemble, that we definitely need to support our arm. And for this, we will see very likely a so-called gravity compensation. And that's the reason why we have this heavy structure around our test bed, where we will see a kind of wire rope-based support system, which will support the space manipulator during its operations. So this is now the vision, the target, the goal for the end of the project. And now I'd like to come to the details of, or the building blocks of the elements we want to integrate into our system. And I'd like to start first with the main hardware elements. And this was already mentioned by Romain, but here I repeat it because we have concrete developments running, and these have to be mentioned here. So we start with the robotic control unit. Here we want to use a representative computer, especially in terms of computing power, such that we are not using too powerful computers for all our operations. One of the main elements definitely will be the robotic manipulator, which is an ongoing development at Airbus Defence and Space, UK. We will also see a tool which will be attached to the end effector or to the flange of the robotic arm, which we call multi-purpose tool. We will also see why it's multi-purpose. It's mainly because it has the capability to exchange the tool tips or tool sockets, how we call it. And these also have to be developed for our specific purposes and the objects we want to manipulate and assemble. On top of that, we will also use this standard interconnect for robotic operations from CNR. This, for instance, will be used for the replacement of some payloads or ORUs, as Romain already mentioned. In principle, they could also be used as walking points for the mobility concept, but this will not be demonstrated in our demonstration. So we will mainly concentrate on the replacement of ORUs and the usage for this purpose of these SI interfaces. On top of that, we will have the objects which we want to manipulate, and in our scenario, this should be the antenna reflector itself. It will consist of some pre-assembled parts, the reflector foil, and there's also some structural elements which have to be assembled by the robotic system, which will consist of two arms. Yeah. So one arm will be our space arm, and another one, just for completeness, will be a standard industrial robotic arm, which we will use to demonstrate two-arm operations. This is not sufficient. We will also see some further support mechanisms or actuators, which we call the workbench. This could be a 3-axis actuator, which enables us to position the antenna reflector in the right position so that we can reach the object from the right side with our manipulators. And this helps us to avoid unreachability with our arms. And last but not least, we will also see some dispensers which hold the elements we want to assemble and which, of course, release them on purpose. And last but not least, we have the infrastructure around it, which will be our test bed, let's say, where everything should be installed and integrated. And here we are currently also developing a gravity offloading system, which will support especially the Whisper arm. And on top of that, we will also see some optical tracking elements so that we can also evaluate the experiments we want to perform. So now I run very quickly through the most important hardware elements, and I'd like to start with the Whisper arm, which is an ongoing development at Airbus Defence and Space in UK at the moment. It's a 6DOF arm following a strict low-cost approach. So that means we want to design and manufacture it as cheap as possible, let's say, but still sufficient for our purposes. That means that we reduce the number of sensors to an absolute minimum, that we are critically looking at redundancy concepts and things like that. At the moment, we are reaching a TL6 of this arm, and we are currently performing the qualification measurements to reach this TL6. This is ongoing, and for EURISE, we will build another model which is dedicated to the EURISE activity. Yeah, and I already talked about the gravity offloading, which we will need if we attach our multi-purpose tool to the flange of this robot. This brings me to the tool. And here we have also an ongoing development, which was started 2 or 3 years ago, and which will continue also in parallel study, parallel to EURISE, and we will also rebuild it and integrate it into the EURISE demonstrator. The main idea here is to have a multi-purpose tool which consists of a central avionics box, including electronics, interfaces, motors, the gear, the drive shaft, and also an end effector camera. So all elements which will be needed for each tool we could consider. What is different, or what might be different, is the tool socket or tool tip of this elements. And here we can imagine to have different elements which are specifically designed for the object we want to manipulate. For instance, a gripper for specific objects. Here, this is a gripper which can hold such an antenna reflector, and we here have from earlier studies gripper or tool sockets which may implement a clamping mechanism, a screwdriver, or other elements. So, and the main motivation here is to save volume and mass, of course. We just need 1 or maybe 2 for redundancy reason of these central MPT elements, and can easily switch between different tool sockets. So this is a basic idea for the multi-purpose tool. And another element, which is also about interface between robotic elements, is the standard interconnect from Senair. They developed it now since 2016 with participation in numerous projects, also EU projects. So it was originally started also in the frame of the Peraspera activities, in the H2020 activities, and they are currently continuing their development. And we will use in EURISE, of course, not their flight segments, which are shown here and which exist in different variations. So here you see one with electrical interfaces, but they can even provide fluidic and electrical interfaces. You can see here the fluidic interface here in the center of the SIREN interface. This is useful for refueling missions, for instance. We will use in our setup the so-called SIREN-C element, which is specifically foreseen for demonstration on ground, and we will use it for the replacement of ORUs very likely. Okay, now let's switch to the elements we want to build. And one potential candidate are antenna reflectors, which might be very large in the future. And here we are talking about diameters of 20, 30, or even more meters. So this is the main motivation of doing this, that we enable a new technology which is beyond the at least the current capacities of launchers. So if we would provide a kind of space factory which would be able to assemble such large structures, we would enable a completely new segment and shift to a new paradigms. This is the basic idea and the motivation also for selecting this use case. And here we also can rely on some prior work, which was mainly performed by my colleagues from Airbus in Toulouse. So they already demonstrated that it's possible with robotic manipulators to assemble such elements. What we now want to demonstrate in EURISE is we want to demonstrate it with the latest developments of space elements, like our Whisper arm and also the multipurpose tool for all these activities, which is a specific challenge because we have to do it with our space arm under 1G conditions. Now I'm switching to software, which is also a lot of work which we have foreseen in EURISE. And here, of course, we do not have these fancy pictures, but I will just summarize the main elements which we will have in this software branch, let's say. We will first have to set up our development environments. And here we will base on the expertise from our colleagues from DFKI, who are already involved in many previous EU projects also, and in the Perispera activities where they already developed a lot of things which we want to adopt and adapt also to our needs. Connected to that is also the question of frameworks which we want to use and which we want to prepare for our purposes. And here it's foreseen also to rely on existing frameworks for onboard software and robotic frameworks. One candidate, and I will come later to that, could be the ESA development of the so-called PASTE system, which is currently available in version 10. And this could be a good candidate for these activities. Based on this, we will set up a bunch of software which will orchestrate all our robotic software elements. And this is what we call the robotic system control software, which is also relying to a large extent on work which we are currently doing in a parallel study called ROSIO, which we will apply here for the first time in a larger application scenario. Then, of course, we will see a lot of elements which are hardware drivers for our hardware elements, CAN bus, the camera drivers, software elements which are needed to control the multipurpose tool and so on. And beyond this, we have a special emphasis on the arm control software of our Whisper arm. So here we are not relying on external or third-party software, but we are looking very close to it and are trying also to implement elements like impedance control just on current measurements and things like that. In addition to that, we will also try to enhance the autonomy of our robotic system. And this, or one aspect of this, concerns the onboard motion planning capability. So we believe that it's a big advantage if we could provide a motion planning capability of our robotic element on board, of course, including collision avoidance and things like that. And for this, we have foreseen to use the expertise from our colleagues from DFKI. Of course, the robotic manipulator is not perfectly precise, so we know that we will need perception and especially computer vision based on camera images to bring the last precision to our robotic activities, especially when it comes to positioning in front of objects or objects we want to assemble or grasp. So this is the perception task, and this will be solved by our partners from Magellan. Last but not least, we will also see robotic ground console software, and in order mainly to test our system, to prepare the missions, to plan it, also to validate and simulate it. So also here we will have contribution from Magellium. And last but not least, we will also see some testbed software, which is about the control of for instance, the gravity compensation facility and so on. And all this should be embedded in an open source strategy we would like to implement or first develop. This is ongoing activities. And for this, we have a partner on board, Libre Space Foundation, which has a specific expertise in the field of open source, and they will support us to implement a proper method. And we will see what we can achieve in this project with regard to this. Okay, quick overview of the main elements. As I already said, we will see a ground segment and a flight segment. On the flight segment, we will have the robotic elements and, of course, the control software for all this. So this will be a large extent of software and hardware developments and usage of existing elements, of course. So also integration is here a big part. On top of that, we will see the ground segment or the communication with the flight segment, or the visualization of telemetric data, but also for the mission preparation. And here it's foreseen to have a kind of copy of this flight segment, which will enable a kind of digital twin. And beside this, we will also have our testbed consisting of software and hardware, which will allow us to drive the experiments. Okay, now let's have a closer look to the software. And the first thing is, let's say, the software framework and also the robotic system control. So we will start with the help of DFKI to set up proper software development tools. We will use existing frameworks, and we will use also several tools which make life easier for the versioning of an heterogeneous software project. And we will very likely be based on existing frameworks which are already known from earlier EU activities, and this could be tasted in the version 10. We at Airbus, as I said already, are currently working on a robotic system control software, and this software should be used for the first time for a large activity. This software, or the purpose of this robotic system control software, is to orchestrate all the robotic elements. And we can see that here, if we have a look at this classical layered approach of onboard software, starting from the board support package, the operating system, also the middleware. And here it now gets more interesting, because we will also rely on existing frameworks and middlewares. And the idea of this robotic system control is to integrate here a software or kind of abstraction layer, which will also later enable us to exchange the underlying framework, not only the middleware, but also the full robotic framework, like not only TASTE, but maybe also ROS, also NASA, CFS could be an option. Or this could be implemented by introducing such an abstraction layer. And on top of that, we will implement this robotic system control, which will have several, let's say, standard elements like database, monitoring and FDIR elements, but also controllable elements. Here we will apply a behavior control scheme to control our mission, and we will also see some intermediate layers to do a more a better task action decomposition to make the complex task more handy, let's say. And on top of that, we will see all the elements of the so-called robotics functional layer, and these are the elements where maybe all our partners will contribute, but also where in the future also other third-party developers could contribute if we follow the open source strategy. So this picture just gives a little bit deeper insight in this robotic system control. It shows more a multi-tier architecture consisting of 3 different levels. Here we have the highest level, which will implement the behavior trees. And here we have the lowest level, which we call the function layer or action or skill level. Here we will see all the interaction with the actuators and the sensors, but also some smart skills might be represented here. And in between, we have a kind of onboard control procedures, scripting language, which allows, with the access to some databases, to help the transition from a more symbolic level to a sub-symbolic level, where all the symbolic descriptions of our mission will be successively replaced by numerical values, which will at the end needed to be to command our actuators. Yeah, and on top of that, we will see the robotic ground console. And for the functional layer, it is foreseen that Airbus will contribute to the arm control software, DFKI to the autonomy and planning elements, and Magellan mainly to the perception elements. Yeah, this slide repeats this more or less. It shows again the arm control software for the manipulator, the motion planning which will come from DFKI, the perception which will be needed to position the robot, and last but not least, we will also see some software to control our test facility. This now brings me also to the ground segment, and here we will also have several software elements. It's mainly foreseen to do it for mission preparation, for simulation, and also to have an exchange between the simulation itself and also our flight segment, which will lead to a kind of digital twin. So it's the idea is to combine the simulation capabilities from Magellan with the flight segment and to combine it to a representative system on ground, which then could be used to evaluate all our missions before we upload it to the flight segment and execute it there. And this brings me to my last slide, and this is about the open source strategy we want to follow. I already said that we are currently developing the strategy, so it's not finalized, and also all the different partners also have to find their position on this topic, because you can imagine that it's not an easy task, especially for industrial partners here. It's also a question on intellectual property rights, also on export control issues. So all these things have to be taken into account and have to be considered to find a proper open source strategy. But what we could imagine at the moment, but this is maybe can change maybe in the run of the project, but what we could imagine is that we will give free this robotic system control, especially the elements which are of general purpose and which are mainly foreseen to orchestrate everything. And then on the functional layer, it could be a decision on a case-by-case decision. So that means we can think of releasing some elements, maybe some basic elements or elements which just rely on industrial or COTS elements for the hardware. And when it comes to more dedicated intellectual property rights, we of course can also imagine that some parts are closed. So this could be a potential open source strategy, but this has to be elaborated in the run of the project, and we will see where it ends at the end. Okay, that's it from my side. I think now it's time for the question and answer section.
Yeah, thank you to you, Mark, Romain, and also to Ingo for those presentation. I think this was quite a comprehensible introduction to what EURISE and the consortium behind it is actually working on. Thanks for that. Sorry or apologies for the little sound glitches in the beginning of the presentations. I think that was rather unfortunate. I hope that for the recording we will make available of this webinar, we can fix the sound a bit. There might be a backup recording of the sound, so none of the contents get lost on the way. Looking to the question and answer pane, there seems to be quite a variety of questions. One question from a visitor, Thilo Behrendt, was upvoted for 2 times, and I would just treat this now as the most prominent one then. Question is, do you aim to include uncooperative customer targets in the mission concepts? I think this question was raised during Ingo's presentation. This is why I assume it's directed to Ingo, but whoever feels being the right person to answer this question, please go ahead.
Oh, okay. If I understand the question correctly, it's about the question if our target objects will be uncooperative. Yeah. So this is, I would say, mainly a challenge for the vision and perception system. I would say definitely we have it in mind, or will not forget this, but it will not be the first step, and it will not be what we will very likely see at the beginning of our activity we have in mind for the assembly of our antenna reflectors. I can tell you that these objects, of course, are very known. So we know the geometry, we know everything very perfectly, and it's even possible to attach also visual markers. So and because of this, we will not make it more difficult than it is already, and that means at the beginning we will start definitely with cooperative targets and also the usage of markers. But you're quite right. On the long run, this will not be sufficient, and and I know also our partners have a lot of activities also addressing this point. I hope this answers the question.
Yeah, I was going to say we can only hope. It's rather unfortunate that we don't have an actual comment function, so that we cannot really go into a dialogue here and only answer this question based on the assumption that we got the question correctly. Let's just hope. Is there anything you'd want to add from your side, Mark, maybe, or should we proceed with the next question?
Yeah, when we speak about missions, we know that also some people refer to uncooperative targets in terms of debris removal and also for servicing mission of unprepared satellites. This is really not the major focus of our activities, because we see that the majority of the systems and markets will probably concentrate on cooperative satellites in that sense. So no catching of tumbling targets or stuff like that. This is not what we are focusing on. We will not size our manipulator nor the control or stuff like that to perform such operations.
Yeah, I assume this clarifies pretty much. Then let's maybe proceed to the question from a user or from a visitor, Sarah T, let's say. Are these modules useful on Moon? I think this question came up while Ingo was showing the components that will be added to the demonstrator.
Maybe I would answer that one. So, for example, the manipulator is already designed with having in mind that some ceilings can be added. Yeah? And beside gravity, this is the most important thing. Sorry. For going onto the Moon. Not for each component this has been considered, so I cannot say that for sure for all the hardware elements, and I think there will be a delta for sure if we go to such a mission. But I would say in principle, yes, they are useful for the Moon. Such a concept, the modularity would work there. Yeah. I hope this answers your question. Otherwise, just place another comment in the Q&A session.
Yeah, that's the workaround. Just add another question. Yeah, then there's the next question. What's the key to the open source strategy? The standardized hardware interfaces or the software that's standardized? I don't know who this question is directed to, but I assume it's also an Ingo question.
So what we have in mind here is mainly related to the software elements. This is where we are mainly working on to establish a kind of open source strategy. But yes, we know that there are also ongoing activities, especially on ISA's side, also to harmonize the different standard interconnects which are available at the moment. It's Cenair is one of it, yeah, and we have them in our consortium, but there are also other companies working on similar concepts, and we know that there are ongoing activities from ISA to harmonize it a little bit, and especially these interface, which should then be implemented by different companies, of course, have to be kind of open source or at least public. Yeah, but this does not mean that everything has to be open source. And yeah, I doubt that this is the purpose of such a standardization activity.
I think when we go towards open source here, our goal is really enable also researchers, enable students, enable small companies to contribute to such a software. This will increase at the end maturity of software, flight software we have available in Europe. And at the end, for us, it's one of the biggest challenges to have all of that running in flight software. And I would like to see maybe in 5 to 10 years, all the student robotic challenges like the European Robot Challenge, like the Spaceport Cup in Germany, and all those challenges are made with quite like flight representative software. This would be really an achievement both for the students and for the researchers to learn from that software, and we will have much more skilled people entering the job market afterwards, but also for the commercial players, because they will contribute to this open source environment. And this is our goal for this open source activity.
Yeah, and I think at this point I can once more emphasize that there will be a follow-up webinar where we delve a bit deeper into the open source aspects of EU RISE, and also in the strategy process that's going on in the background. We didn't focus too much on this today, but the open source strategy is a huge component of the EU RISE project. So if you're interested in the open source aspects, there will be a follow-up webinar. So that being said, going on to the next question, have you identified use case KPIs for ensuring that the assembly operations make useful products? Yeah, whoever feels apt for answering this.
So this reflector design, for example, is based on business cases we have assessed in the past. So we're confident that this is a viable product for a commercial market. But it's not actually the goal of this particular project to assess at the end again the commercial attractiveness of this reflector. Omar, maybe you want to complement.
Yes, let's say that we consider the reflector as a use case because it's a product that can be used on different markets. We can use it for science, for telecommunication, or for even military operations. So it's a use case that cover a lot of the market. And also it's a complex product. What we try to do is to more design the reflector in a way that the process of assembling is compatible with other kind of assembly. With our concept, for example, it's possible also to assemble some structure or to assemble other things than a reflector. And so this is where we also try to include this modularity concept in the interface definition to make sure that the operation are not just applicable to this reflector, but also to other kind of structural assembly or subsystems.
All right, thanks, Rona. And now looking at the time, there are 3 questions focusing at the end-to-end demonstrator. First question, what conditions can it replicate? Then what tier L level will it achieve? at the closure of the project if the project is successful? And will it be open to test other components which use the same interfaces as the ones described earlier? Maybe this can be answered in a wrap-up sort of thing.
Yeah, so maybe starting with the last question, will it be open for other components? I would say in principle, yes, yeah, but feel free to reach out to us. We will discuss it internally. I mean, inside the consortium, if this adds additional complexity for us in the demonstration or not. But in principle, we can discuss everything and then we can see in which direction we go. But they cannot give you a clear yes or no at this stage. Then the next question was the TRL level we would achieve. Actually, we have not foreseen to have a TRL assessment. Yeah, so all of the building blocks are already on TRL 4 to 6. This is the status of all the elements. Yeah? And I would say that this is a quite realistic environment, but on the system level, of course, it's nothing with a thermal vacuum chamber or something like that. Yeah, but for that, it is close to TRL 5, yeah, because we have a quite realistic setting, but the environmental part is definitely missing. We would normally see for a component development. Then what was the other question?
The conditions the demonstrator can replicate, I believe, is the one that's missing. Which
okay.
you have answered right now.
Yeah, exactly. Yeah. So you have maybe seen on the pictures of the testbed we already setting up in our lab that we will include some darkening cloak just to have a visual representative environment, which is important for our algorithms. But we will not have, beside that, some environmental conditions like thermal and so on. Okay, then the questions we have left are, do you have an overview?
There's one targeting the open source strategy. Is the open source and open collaboration strategy only open for software and universities? Innovative HW from startups could be interesting, but I did not hear it.
So first of all, as I said, the open source strategy has not been fully performed yet. Yeah, so this is also part of the work we have to do. But I think it will not be restricted to just to universities or so. It's the idea is to provide at least basic framework which also allows others, and others are also partners, and that means also including also companies, which can contribute to future projects in order to make it easier to collaborate. That's the basic idea.
Yeah.
We see really the gap when we look at the flight software frameworks. We have, for example, Space ROS, but it's not fully qualified. You cannot use it for each mission. That's our understanding. And we have that with other frameworks as well. So with the definition Ingo presented, it's possible to use several of those frameworks. And the best scenario would be that we have an open source environment in which we see plenty of universities and companies contributing to, because it needs to be as powerful, of course, not with the same attendees, but similar to what we see with ROS on Earth. And if it is just a half open shop, it will not be established like that.
And as I said, it shall not be a substitute to something like ROS or so. The contrary is the case. We will rely on existing frameworks, but we try to be as flexible as possible by introducing such a framework abstraction layer, which allows us to exchange the framework. Because we also know that also different customers may have different requirements, and we also would be in the position to react in a flexible way to these requests. Yeah. So that's why we are also looking at solutions from NASA, like the onboard software CFS. Space Rose, of course, is also a candidate. But also on European level, the TASTE system, which was also the basis for the predecessors on EU level.
All right. I don't see any more questions popping up in the Q&A section. So I would say let's call it a webinar at this point. I can hint you on the fact that there is actually various ways to get in contact with the people behind EURISE. There's an email inbox, contact@eu-rise.space. So if you have any further questions, feel free to reach out to the project consortium. And as I said earlier, there will be a follow-up webinar where we delve into the open topics of today's session. Yeah, I'd leave it to Mark Mans, the project coordinator, again to say some final remarks for the closure of today's session. And thanks for attending from my end.
Yeah, thank you for the moderation, Thomas. Thank you for the presentations, Ingo. Thank you to all of you for your interest. I think this will grow over time. And as Thomas mentioned, the real webinar about the open source strategy will follow later. So stay tuned if you want to get those updates, which could be interesting for you, and contact us if you want to collaborate. We are really open to that. Yeah. Thank you and have a nice day.
Thank you. Goodbye.
Bye.
Bye, everybody.